Hello students, welcome back. And let's go to problem 2, hypothesis testing problem, which was continued from the previous problem, which was about confidence interval. The article Development of Novel Industrial Laminated Planks from Sweet Gum Lumber, Journal of Bridge Engineering 2008, 6466, described the manufacturing and testing of composite beams designed to add values to low-grade sweet gum lumber. These are the sample statistics, and this is what we got. 30 trials of observation or experiments, and then the average we got, the mean, is 7,203.091 pound per square inches, and the standard deviation, the sample standard deviation was 5.42.540. All these are coming from samples, so these are sample statistics. Now here's a question. Does the sample statistics suggest the mean modulus of rupture exceeds 7,000? And this 7,000 did not come from the sample study. These came from samples, all right? These are sample statistics. This comes from problem set. So this is the null. All these are coming from samples, so throw them away or nullify them. You still have 7,000. So this is the null. And then how about the alternative hypothesis? It's always either greater than null or less than null. In this case, 7,200 something is greater, so it should be greater than null. Also, here's another keyword, exceed. That means you have to do greater than null hypothesis. Okay, all right. Let's go to the solution. And this time, let's use the probability value approach. Step 0, you have to make decision whether to use z-test or t-test. In this case, it's going to be a t-test. Reason number 1, the original distribution is believed to be normal or normal-like. Why? Because this is coming from experiments, observations, so clearly it's going to be normal. We do not expect any kind of systematic bias here. Second criterion, the original standard deviation is unknown. Unless you test every single lumber products, break everything in the earth, you're not going to get population standard deviation. So it's unknowable. And we have relatively small sample size. We test only 30, and the usual threshold I'm using for this class is about 100. And sometimes we can use z-test for as low as 50. Oh, 50 is too small. I don't like it. 100 or bigger, okay. I'm relatively comfortable with using z-test, but less than 100, you should be t-test. By the way, just a little bit of digression. If you use some old textbook, some old textbooks use n equals to 30 as the threshold. Greater than 30, we use z. And the less than 30, then you use t. That's because those textbooks are old or copied from older textbook, which was in turn copied from even older textbook. 50 years ago, we didn't have much computing tools, so people used to do these. But nowadays, expectation for computational, the computing tool is much higher than what they were 50 years ago. So n equals to 30 is nowadays considered as small sample. Anyway, his hypothesis, and then sample statistics of sample size of 30, so degree of freedom is 29, and the sample mean and sample standard deviation. Okay, SE, standard error is S over square root of n, or maybe I'll write it SE is standard deviation over square root of n, and that goes to the denominator. Okay, all right. Now let's draw the initial picture. Looks like this. The null is 7,000. Let's open up the hypotheses again. Null is 7,000. You see that's 7,000. So that goes to the center. And then where is the sample statistic? associate is to the mean, 7,203, and that's to the right. And then let's find out this probability here, the purple part. Calculate this probability, and then let's compare that with this level of significance of alpha. And if this purple is greater than alpha, which means there's significant probability we can still have something like this even though null is right, then we go with null. And then if this is small, which means there's very little chance that null is correct, yet we get that kind of result, in that case we go to alternative hypothesis. You see, theoretically, this method is a little bit difficult to follow because you gotta know the idea of probability, or more precisely speaking, the idea of conditional probability, because these are both conditional probability where a condition is null is correct. Condition is null is correct. And then associated type 1 error. Oh my, I'm going to be too deep. And despite our textbook author's preference to this method, personally, I do not want to emphasize the probability method. It's not my style. You can do all the computation like this, great. But then again, interpreting, that requires some higher skill. And if you're good at all those higher level mathematics, great. But most of the students in 1680 are not good at those kind of higher mathematical skills. So personally, I'd prefer to emphasize the first method, the critical value method. Anyway, this is the setting, and let's continue. Roughly speaking, by the way, this p-value here is probability that null is right, roughly speaking. Okay, let's find out. Let's find out the t-statistic. N minus center over SC. Let's increase the font. N minus center over SC. So N, 7,203 minus center, 7,000 over SE. S over square root of N. Calculate that whole thing and run your calculator. You end up with 2,005 something. And then again, using some scientific calculator, another expensive tool, if you calculate, you're going to get 0.97 something, and you can find out this p-value. Turns out to be 0.024 something. And then what do? You did this t-score computation, good deal, and then you did this p-value computation and got up to here. Now what? What does that mean? Roughly speaking, this p-value is the probability that null is right. And the probability that null is right, roughly speaking, is pretty small. And so small that it's less than alpha value of 0.05. So the implication is probably null is not right. Null is probably wrong because the probability is much smaller than alpha. Indeed, therefore the conclusion is we reject null and accept alternative hypothesis because 0.024 is less than alpha value of 0.05. See, alpha is 0.05 and observed probability that null is right, roughly speaking, is 0.0247, less than alpha. So the chance is null is not right. Null must be wrong. Now, if you're comfortable with this probability approach, go ahead and use it. I'm not going to stop here. But let me come back to this critical value method again. Computation may be a little bit harder. But the interpretation is easier. This is sample statistics. Okay, I didn't have to run it again. Here's a picture. And this is a little bit different. We have null and we are looking for the threshold, critical value. Okay, and 7,203. This value I don't know where it goes yet. Depending upon what this value is, this absurd mean may fall into null region, which is pictured in blue, or it may fall in alternative region, which is pictured in red. It all depends upon what this critical value is. And let's calculate the critical value. And here we go, n minus center over SC, n minus center over SC we have over here, which is equal to 1.699. Same way you calculate using the t-table, and then solve this equation. Use some algebra. You get 7,168, and consequently you can compare that value with the observed mean of 7,200 something. Here's the summary: 7,168. Once you find out this critical value, you know where to put 7,203. Now in this picture, it's now easy to determine, does it look like this is sufficiently far away from the null? Or is it close from the null? Null is over here, and how close is it close? Closer than the critical value over here is considered close, and farther away than critical value, this part, red part, is considered too far. So too far from null, so null is wrong. Accept alternative and reject null. And this is the idea behind the critical value approach. The computation is, in my opinion, about push, or even easier still, yet the interpretation is much easier. Let's go back to the probability method again. Initial picture goes like this. Instead of a known endpoint, we have known endpoint here, 7,203, the observed mean. That's easier, okay? And that allows you to calculate the t-score precisely, n minus center over SC, and get that. And then your trouble begins now. You have to calculate this probability that t is greater than, oh, wait a minute, this is, excuse me, t is, sorry about that, t is less than that. This green part is 0.976. You see, I hope you see a point here. It's complicated, so complicated that I even made a mistake here. Trivial it may be. Okay, so this number corresponds to the green part. So in order to find out this purple part, 1 minus of that, and once you get this number, another analysis, what does that mean? Compare with alpha, and then greater than alpha, what does that mean? Less than alpha, what does that mean? You have to think again until you get the right conclusion. You can do it, yes, and it works, and certainly it is loved by our textbook author, but not me. I do not want to emphasize this probability value method. I think the solution 1, the critical value approach, is superior.